Hi, I welcome you back. Welcome to the portal. In this video, we're going to talk about electric fields. Okay, so now there's a definition that you can pause the video and read it or write it down. Okay, so what is this electric field? It is a region of space in which a charge will experience a force. Okay, and the direction of the field at a point in space is the direction in which the positive charge would move if placed at that point. Okay, so what it simply means is that it is a point somewhere in space around a charge whereby if you place a test charge, the test charge will experience a force. Okay, and then the direction of those field lines will determine by the direction in which the test charge will move. If the test charge placed near a charge, if it moves away from the charge, then it means that the field lines of that charge, they move outwards. And if the test charge moves towards the charge, towards the center of the charge, therefore it will mean that the field lines, they go inwards. Okay, so now this, we have a diagram of the definition here. So this is a test charge. Okay, so now the reason we are seeing field lines going out is because of this test charge. When it is placed in space around this charge, it is being repelled outwards, okay, away from this charge. If this charge was placed here, okay, it will be repelled to that direction. And if it was placed here, it will be repelled in that direction. Remember, positive and positive, they repel each other. Okay, so now this is the field line of a positive charge. They go outwards. Okay, so another definition that you can look at is the electric field at a point is defined as the electrostatic force experienced per unit positive charge placed at that point. Okay, so what does it mean? It means that E is equals to F divided by Q. Okay, so electric field at a point, it is the force experienced per unit positive charge at that point. You see, per unit positive charge. So the force is experienced, right, per unit positive charge, okay, at that point. So it simply means this. So this definition is a little bit easy to grasp. Okay, so now if we check the negative charge field lines, so negative charge field lines, they go inward. So meaning if this test charge is placed here, it is going to be attracted towards the center of the charge. So also if it was here, it was going to be attracted towards the center of the charge. You see, so because of the direction of the test charge, when it is placed relative to the charge, it determines the direction of field lines. So it tells us that the field lines of this charge, they go towards its center, they go inwards. Okay, so now when you are being asked to draw the field lines of a negative charge, you will do that. Okay, they go inwards. Okay, okay, so now another thing that you have to keep in mind is that the number of lines, they show us the magnitude of the charge. Okay, so the lower magnitude of a charge will have fewer lines. Okay, and then the one with a higher magnitude will have many lines. So the density of those lines is going to be higher. As you can see, this one has many lines compared to this one. Okay, so if they're telling you that you have 10 newtons and 1 newton, so there must be a difference between the field lines to show that the other one has a larger magnitude. Okay, if you don't do that, you're going to get penalized. Another thing that you have to look at is between two fields of charges. Okay, so if I have a positive and negative, so remember that positive and negative, they attract each other. Okay, and that the field of positive charge goes outwards and then the one of negative charge goes inwards. So if they are placed close to each other, this is going to happen. Okay, so as you can see, they go out of the positive one, they go inside the negative one, you see. And then these ones at the side, they also want to converge, but then the field is weak at this point because the distance is greater at this point. Okay, so and then here you can see that here we have negative, so the field lines, they go inside all of them, but then negative and negative repel each other, you see. So instead of them connecting, they don't connect, you know, they repel each other, you see, they repel each other. So similarly, if you had a positive and positive, the same thing was going to happen. Okay, the same thing was going to happen, but how will it happen with a positive one? With a positive one is that the field lines were going to point outwards. Okay, they were going to point outwards, you see. So these are 3 marks. You can get 2 marks or 3 marks just to draw this. Okay, so I believe that everyone knows how to do this. Okay, so you should be able to do this. So now the definition is the one that we did at the top. Okay, so it says the magnitude of the electric field E at a point can be quantified as the force per unit charge. Okay, so sometimes in multiple choice they can say force per unit charge. You have to know that, oh, it's electric field, you know. And then so where F is the coulomb force exerted by a charge on a test charge. Okay, then the units of the electric field are newtons per coulomb. Very important, newtons per coulomb. Okay, so you have to keep that in mind when calculating electric field. So now as we are given this equation, so we also have this equation to calculate what electric field. Okay, so this equation is derived from that one. Okay, so now this one, it's used to calculate the electric field that you will feel when you're at a point, okay, due to some charge Q. Okay, so now the net electric field can be calculated, so but it is the sum of electric fields on a point. Okay, so electric field is a vector quantity, and then this is the general formula. What does it mean? It means that if I have a point charge here, a point charge here, and then here I have a point of interest, point P. Okay, so if now this charge, it has electric field and this one has electric field, so but what is the net electric field that I'm going to feel here? So it is the sum of these electric fields. Okay, so remember that electric field, it is a vector quantity. Okay, so being a vector quantity, even though I say it is the sum, at some point we'll find that the direction says negative and stuff. Okay, so we'll get to that. And then now always choose direction when solving an electric field problem. Okay, so if I have, for example, I have a positive charge here, I have a negative charge here, and then I have point P. Okay, so what do we know? We know that when I'm at point P, so if I focus on this positive one, right, I know that the field lines of this positive one, they go outwards. Okay, so meaning the electric field that I'm going to feel at point P is going to be towards the right. So now this one, I know that it is negative, and then with respect to the P, the field lines will go inwards. Okay, so it will go towards the left. Okay, it will go towards the left. Okay, and then now if I choose direction, for example, if I say choose to the right as positive, what is going to happen is that when I do my net electric field, I will say E net is equals to E1 plus E2. Okay, so this is the general formula. But then now I'm going to choose my signs now. So which one is towards the right? This one is towards the right, and I say the right is positive, so it's going to be E1. Okay, so plus E2. E2, it will be this one. Okay, so this one is towards the left. It means the left is negative because I chose right as positive. So I'm going to have negative E2. Okay, so you will see that I will have E1 minus E2. This is my net electric field. Okay, so the direction you choose it with respect to this point. Okay, do not be confused by other field lines like the one that is going that direction. We are not interested in that direction. We are interested in this direction. Okay, so we are interested in P, you see. So but now what is the net electric field? Net electric field, it will be given by a vector, a resultant vector of these two vectors. Okay, so it will depend on the magnitude where it's going to go. Let's say for instance it goes to the right. Okay, so even though here we have E1 minus E2, we will have E net to the right, which is positive. Okay, and if the E net it becomes negative, we are going to conclude that E net is going to the left. Okay, so we have an example there. Calculate the electric field strength 30 centimeters from a 5 nanocoulomb charge. Okay, let's do it, guys. Okay, so which equation of, or let me say which formula of electric field are we going to use? Okay, so first of all we have to identify our data. Okay, so our data, we have Q, which is positive 5 nanocoulombs. Okay, so and then now the distance is what, 30 centimeters. So R 30 centimeters. So 30 centi, this centi you change it, you say times 10 to the power minus 2. Okay, so it has to be in meters. So now it is in meters. Okay, so we are going to use E is equals to KQ divided by R squared. Okay, so K, 9 times 10 to the power 9 multiplied by Q, 30 times 10 to the power, multiplied by 5 nanocoulomb divided by 30 times 10 to the power minus 2 all squared. Okay, so that is the basic calculation of how to calculate electric field. Okay, so 9 times 10 to the power 9 multiplied by 5 times 10 to the power minus 9 divided by 30 times 10 to the power minus 2 all squared. So going to have 500 newtons per coulomb. Okay, remember that the units for electric field is newtons per coulomb. Okay, so because they did not say the magnitude only, so now it is 500 newtons per coulomb to the right. Okay, or towards X, or east to the right. Okay, but we must have chosen direction and say that choose to the right to be positive. Okay, so let's do example 2 now. So example 2, we have two charges there, and then we have a point of interest which is X. Okay, so now we say two charges Q1 and Q2 are separated by distance 50 centimeters. What is the electric field strength at a point that is 20 centimeters from Q1 and 50 centimeters from Q2? Okay, so the point lies between Q1 and Q2. Okay, so but then here the distance they said 50 centimeters. Okay, and then here they said 30 centimeters. Okay, so what is the they are separated by 50 cubic centimeters. Okay, Q1 and Q2, but here we can see that they're separated by 40. Okay, what is the electric field strength at a point that is 20 centimeters from Q1? Okay, so this one, it was supposed to be 20, but now it's 10. Okay, and Q1 and Q2. Okay, and 50 centimeters from Q2. Well, let's decide. We're going to use these ones here. Okay, the ones that we see. So first of all, let's write our electric field diagrams. Okay, so here we know that we are talking with respect to x. Okay, x is in the middle. So now we know that this positive, the field lines, they go to the right. Okay, so this is x. So x is going to experience a field line from Q1 that is going towards the right. Okay, and then what about Q2? Q2, we know that negative, it has field lines that go inside. Okay, so also the field line will go to the right. Okay, so now I can say choose right is positive. Okay, so now here I just cut the problem in what is the electric field strength at point. Okay, yeah, there's a question. Okay, so they want the net electric field here. Okay, so the net electric field at that point, we know that the equation, it will be E net is equals to, all of them there to the right, E1 plus E2. Okay, so now E1 is given by K Q1 divided by R squared. So 9 times 10 to the power 9 multiplied by what? Multiplied by 3 nanocoulombs. 3 nanocoulombs divided by, what's the distance? Let's use 10. Okay, 10 centimeters. 10 10 centimeters all squared. Okay, so now here 9 times 9 to the power 9 multiplied by 3 is 10 to the power minus 9 divided by 10 times 10 to the power minus 2 all squared. Okay, so I'm getting 27,000 Newton per coulomb for E1. What about E2? KQ2 divided by R squared, and then 9 times 10 to the power 9 multiplied by Q2. Q2 is 4 nanocoulomb. Also here we only include positive values. 4 times 10 to the power minus 9, okay, divided by the distance 30 centimeters. 30 times 10 to the power minus 2 all squared. So okay, so now the magnitude of the electric field there is 400 Newton per Coulomb. Okay, so now we go to E net. E net is going to be 27,000 plus 400. So we're going to have 700 plus 400, okay, 3,100 Newton per Coulomb. Remember, we chose positive to the right. Okay, so therefore 3,100 to the right. Okay, so this is our answer for this example. Okay, so example 3. So example 3, the right angled triangle comes back again. Okay, so now the statement reads as follows: 2-point charges form a right angled triangle with the point A at the origin. There are charges Q2 and Q3. Okay, the distance A, the distance between A, Q2 is that. Okay, A and Q2 is that. Okay, yeah, so let's just focus on the diagram. Okay, so now we have a right angled triangle there. Okay, so this is our A, 0.03 here, 0.05 here. Okay, so now here we can see that Q3 is negative and Q2 is positive. Okay, so now because this one is negative, we know that the field lines of negative, they go inside. Okay, so it goes upward, and then here we know that this one is positive. The field lines of positive, they go what? Outwards, so they go towards A. This one goes away from A. So if I was to combine those two vectors, I will have this. I will have this head to with using head to tail method. I will have this, and this will be my resultant. Okay, this will be my E net. Okay, so now this one will be E2, and then this one will be E1, E3, E3, E3. Okay, and then E2, E3. Okay, so now this is a right angled triangle. I'm going to use what? I'm going to use Pythagoras theorem. Okay, so now let me go and do that. Okay, let me rewrite it very nicely here. Okay, this is E net, this is E3, this is E2. Okay, here I have right angled triangle. So now let me choose my direction. Okay, so I'm choosing up and to the right as what? As positive. Okay, I'm choosing up and to the right as positive. Okay, or I can choose to the left as negative. It's fine. Okay, so now First of all, I'm going to calculate E2. Okay, KQ1 over R squared is equals to 9 times 10 to the power 9 multiplied by, actually it's Q2 here, multiplied by Q2, 6 nanocoulombs, 6 nanocoulombs divided by 0.05 meters all squared. So here I have 21,600 Newton per coulomb. What about E3? Okay, Q3 divided by R squared. Okay, divided by R squared. So 9 times 10 to the power 9 multiplied by Q3 is 3 nanocoulombs. So we're going to take the magnitude 3 nanocoulombs divided by what? Divided by 3 centimeters, 0.03 meters. Okay, 30,000, here I have 30,000 Newton per coulomb. Okay, so now, and then E net, I'm going to have the square root of the square root of that. So here I chose to the right as positive, and this one goes to what? To the left. It's E2. Okay, E2 goes to the left. So minus E2 all squared plus this one goes up. So up, I say to the it's positive. So E3 is positive plus E3 all squared. Okay, so now E2 is 21,000 so it's 21 times 10 to the power 3 all squared minus 21 all squared plus 30,000 30 times 10 to the power 3 all squared. So it gives me one. Okay, I'm getting 36.62 times 10 to the power 3 Newton per coulomb. Okay, this is the answer. Okay, so now okay, so now they did not explicitly say that they want the magnitude, so it means they want direction as well. So they want magnitude and direction. Okay, so if they had said calculate the magnitude, this was the final answer, but then now they just said net electric field, so meaning we are going to calculate the angle of this net. So it's going to be arctan of E y component divided by E of what? Of uh, x component. Okay, so now here I'll have the y component is what? It's positive 21,600. Okay, 21,600 divided by actually no, that is 30,000 at the top. We need to 30,000 at the top. 30k at the top, and here 21,600. 21,600. Anyway, here I think there's a mistake here, because 21,600 is 21.6 here. So this answer okay, because in here it's supposed to be 21.6. 21.6 times 10 to the power 3. Then okay, so here we have 36,97 times 10 to the power 3 Newton per coulomb. Okay, so now here E3 is y, and then E2 is x. Okay, so opposite over adjacent. So now theta is what? Like tan of actually it's negative here. Okay, P9. So we have a reference angle. We actually have a reference angle of 89. Okay, so so meaning that here we have a reference angle of 89.96 degrees. Okay, so this is the reference angle, and then now meaning theta nh degrees plus so meaning our theta is 90.04 degrees. Okay, so that will be your direction. Okay, now problem 1. Okay, this one comes from past paper. Okay, so I think I'm going to do this one on a separate video. Okay, so let me conclude this video here.